This is the lecture for 15.1, double integrals over rectangles. And before we get started here, I just want to ask you to bear with me. It's still a little tricky to use this new setup to deliver lectures, so it might be a little rocky, but I think we'll get through it. So the idea of this section starting out is that we kind of want to extend the idea of integration now to multiple variables, to integration of functions of multiple variables. So I think the easiest way to understand how we might do that is to first remember, what does integration look like in Calc 1 when we have a function of one variable? So let's remind ourselves, let's recall the following. The area problem in Calc 1. The area problem in Calc 1 said if I have a function whose graph looks, I don't know, maybe something like this, that function is f of x, how do I figure out the area under the graph of this function f of x from some starting point A to some ending point B in its domain, right? The x-axis is the domain of f. In this case, it's an interval or a line of input values. Right, this is going to be important to think of things in these general terms if we want to extend this idea of integration that we have here to an idea in multiple variables. So let's start out there. We have this function. In Calc 1 we said, well, to figure out the area under this curve, we would take the integral from A to B. But what did that mean? It meant we actually, if you remember how we defined the integral from A to B, the definite integral, it meant we chopped this interval of values into n pieces. And typically we took this with equal size little pieces. We'd call the size of each one of those delta x. So maybe I just kind of indicate that here. The size of each one was delta x. Sorry, that's a little small. I'll write it bigger here. And if you think about that, the size of one of these little pieces, if the interval from A to B was chopped into n pieces, how big would that size be? Well, it's just the length of that interval, which is the ending point minus the starting point, divided by how many pieces you chopped it into, right? So b minus a over n is the size of each one of those little delta x pieces. So when we were integrating, that's where we started. We chopped this domain into a bunch of little pieces, n little pieces, each of usually an equal size, delta x. And then we said, okay, well, then all I have to do to figure out the area under this thing was to first approximate it by looking at each little interval. Maybe this is the ith interval, where I could be 1, 2, 3, right? I could be 1, 2, 3. And it could be any value from 1 to n, the number of pieces we have. But if we look at an arbitrary one, the ith one here, the idea is, well, we take some point in there, usually we call that xi star, and that was called a sample point, and then we would actually see how tall the function is at that sample point. Right? The function height would be f of xi star. And then we actually just put a little rectangle over this interval, the ith interval, and we say, okay, well, it's a bad rectangle, but that little rectangle approximates the area under the curve just in this little interval. And then so we say, okay, well, do that, but do that for every one of these intervals. The first one, I equals 1. The second one, I equals 2. All the way through the nth one. So you're putting these little rectangles over every little interval to approximate how tall it is. How tall or how much area there is under the curve there. Sorry for my rectangles. They're not great. Okay. And so if you add up all those areas of all those rectangles, you approximate the area under the curve. So you could say the area is equal to kind of like all these things added together. So I'm going to start out by saying a description of all those things added together for every interval I equals 1 to n. So that's hitting every interval. We add up the function value at the test point, the sample point in the ith interval. So that's actually just the height of this rectangle. And we're going to multiply it by delta x, the width of this rectangle, to give us height times width gives us the area of that rectangle. So we multiply the height f of xi star times that constant width delta x. We said, okay, well that sum, that's adding up all those areas of all those rectangles from A to B. That won't be exact, but if we take infinitely many divisions, it becomes exact. So we take a limit of this as n, the number of divisions here, goes to infinity. Right, and I know that was kind of a long recap on how integration works, but it is very important to remember that this is how we defined the definite integral from A to B of a function f of x dx. Right, so let's recap really quick here. First, we chop the domain region, well, let's say it this way. We chop the region of integration in the domain into pieces of equal length. Next thing we did was we add up. We add up the function value at sample points in each division, in each piece. Right, so that's our f of xi star. That's the function value at the sample point times the length of each piece, delta x. Right. That gave us the area under this ith interval, or under the curve over this ith interval. Add those all up, and you get the approximate area over the entire curve from A to B. And then finally, take a limit as the number of pieces goes to infinity. In this case, our number of pieces was n. We chopped this up into n pieces. So we took n to infinity. Right, so that was the general procedure, and this is actually going to let us very maybe intuitively define double integration, integration of a function of two variables over some region in its domain. So let's see that right down here before we go on to another video. Okay, let's see that here. Now might be a good time to take a little break, or if you're ready, just let the video keep rolling here. So let's try to remember the process that we saw up here for integration and see how we do that for a function of two variables. This is real Calc 3 stuff now. We just recapped the Calc 1 case. So In this case here, we're going to do the same general procedure, but let's think of the picture first. We have a function who's got some graph, right? We know these functions of two variables have surfaces as their graphs. So that surface is now kind of taking the place of what we had here in this curve, right? That was the graph of a function of one variable. Now we've got a surface as the graph of a function of two variables. So the idea is going to be the same, though. We want to figure out kind of what's underneath that but above the domain. Right, so let's do that same procedure here. Let's find what's beneath this surface but above some region in the xy plane, in the domain of this function f. So if I think of it that way, I can think of maybe there's just some region from a to b in the x direction, but now also some c to d. Let's make it even further out here. Maybe some c to d, oops, in the y direction. Maybe I'll label things here. Let's make this look a little better, move my c value. Let's look better there. Ooh. So it might be a little rough, but hopefully we can see what I'm trying to describe here. Let me emphasize maybe with a different color that what we have is this surface up here. Now I'm going back over it in blue. But we're only keeping the portion of it that sits over this little rectangle that I've formed in the xy plane in the domain. Right? Just over this little rectangle that goes from a to b in the x direction and c to d in the y direction. We're going to call this little rectangle, we're going to call this little thing rectangle R. So the way I could describe that rectangle is the set of all points in the plane so that x is between a and b and y is between c and d. Right, that's the description of this little rectangle R down in the xy plane. And we're just saying that let's just consider the portion of this graph of our function f that sits above that rectangle. We're not looking outside that. That's kind of the equivalent of this interval from a to b here that we looked at for a function of one variable. That becomes a rectangle when it's a function of two variables. Right, so you can think of if the area problem had us finding sort of what's beneath the graph but above the domain, now that same sort of problem here is going to actually have you, when you try to find what's beneath the graph, the surface, but above the domain, that rectangle R, what you're getting is the volume. So equivalent to the area problem now is finding the volume below the graph and above R. Now this does assume that our function is positive, that it never dips below the xy plane. That graph never dips below the xy plane in this rectangle. So let's make this clear. We are assuming this. Okay. So how will we do this? Well, we're going to follow this exact, if we want to find the volume below the graph, but above this rectangle R, how are we going to do it? We're going to do it exactly the same way we did it up here, finding area. Let's chop the region of integration in the domain into pieces of equal size here. Up here is equal length, but notice our region now is some sort of area. We're going to have to chop these into little pieces of area. We'll choose to make them of equal area. So the way we do that is exactly what we did before. We just take this interval from A to B and chop it up into m pieces. Right? So here in this case, I put what? 1, 2, 3, 4, 5, 6, however many little divisions. In general, we describe the number of divisions in the x direction as m of them. And we also chop up the division, the part in the y direction. We say however many we chop that up into is going to be n pieces in y direction. If you think about what that would do, if I kind of thought of all these divisions chopping up my rectangle, those are going to look like lines kind of coming across, sort of like this. I've got to work on my drawing skills here. Right. This first division is like this first strip of the rectangle. The second division is like the second strip. But if I do that from the other direction as well, then it chops this up into a bunch of little rectangles. And that's what we want. Imagine those being squarely oriented in rectangle R. I know they look a little off kilter. But just like up here, we considered chopping into n pieces. Well, here now we see what these little pieces would look like. They'd be little sub-rectangles. So let's describe one of those little sub-rectangles, maybe the ijth one. So we're saying, if we say rij, we're saying the ith location, the ith interval in the x direction, and the jth interval in the y direction. So I could be anything from 1 to m, j could be anything from 1 to n. So let's describe that thing. Maybe that's where it sits. Maybe we're looking at, I don't know, the 1, 2, 3, and 1, 2, 3. This would be R3, 3, it looks like. So that's I equals 3 and j equals 3. But the idea here is the same as it was above, right? We've chopped up this region into, let's see how many. We really didn't even say how many. There are, well, we have m pieces this way, n pieces this way. There are m times n divisions of this rectangle R, each one labeled Rij, where I is some number between 1 and m. So it's one of these intervals, one of these m intervals along this direction. And the j value goes from 1 to n, one of the intervals along the y direction. But notice that's going to make a grid of m times n little rectangles, called each one called Rij, for some value of I and j. Well, that's the first step up here. Chop the region of integration into pieces of equal length. Let's take a look what we did over here. After that, we sampled the function value at some test point, some sample point, xi star, in each of the intervals from I equals 1 to n. Excuse me. So we're going to do the same thing down here. We're going to sample each of these little Rij's at some test point inside. So I've drawn a little blotch there. Let's undo that. Maybe do it in a new color. There's my little sample point. We'll call that thing, we'll call that Xij star, Yij star. oops, xij star, yij star. Just like we named the sample point up here based on a subscript indicating which little piece it came from and a star indicating that it's a sample point. Usually when we leave off the star, that's referring to these divisions themselves. A sample point is between some of those divisions potentially. So we put a little star on it to specify. But then from here, the idea is, okay, well, we're choosing these sample points, and if I take the function value at this point, I land at some position on my surface. Now the position of that point would be xij star, yij star, f of xij star, yij star. Sorry about that. Kind of running off the page there a little bit. Right? That would be the location of this point. But notice the z-coordinate's just given by the height of the graph there, the function value there. So just like above, we made little rectangles coming down from that height. Here we're going to make little rectangular prisms coming down from that height. So just think of a flat little prism at whatever height that dot is, coming down, coming down. The little tower, right? Something like that. And so the idea again is, okay, we sampled each of those, we sample each of the ijth ones of the Rij rectangles at some sample point, xij star, yij star, to give this sort of idea of what height should this little tower be so that it gives us the volume underneath our surface, but just above this little Rij. And we do that, and then we add up what we get from that over every single one of these rectangles. So we do it for I equals 1 through m and j equals 1 through n. And this is represented by what we call a double Riemann sum. But this is like the second step here, where we added up the function value at all the sample points, and then we will, it looks like multiply by something. We'll see about that. But so we start out by saying the volume should be, just like we did before, a sum now, but now it's actually two sums, because you go from I equals 1 to m and j equals 1 to n of the volume under the graph above Rij. That's the idea. Add up all the volume under the graph above each one of these little rectangles for I equals 1 through m, j equals 1 through n. You get every one of them. That should be the total volume under our surface above this rectangle R we started with. So let's just figure out how we do this. Well, we'll do it the same way as before. Eventually, we're actually just going to compute the volume of each of these little towers here, and then take the number of towers, the number of pieces we chopped it up into, to infinity. So let me just jump to that right now, not put that off. Let's just go ahead and say eventually we're going to do this by taking m to infinity and n to infinity. Oops. And what are we actually adding up? Well, we're going to add up the volume of each tower, which should be the height of the tower, which we know is just the z-coordinate, the f of xij star, yij star. And we need to multiply that by kind of this cross-sectional area, which is just the area of Rij. So let's write that down. Let's multiply that height times the area of Rij. Well, up here in the previous case, that was just our delta x, right? That was just the size of the division, the size of the piece that sample point came from. Well, up here, or down here, now the size of that piece is really an area. It's an area of one of these little rectangles. But if we think of chopping this direction into little pieces of length x, computed the same way as before, and this piece as being chopped into pieces of length delta y, again computed essentially the same way as before, then we can describe what the area of one of these little pieces is going to be. In the x direction, the Rij is going to be length delta x, and in the y direction, it's delta y. To get the area of a rectangle, you're just multiplying those together. So we know we could write this as, maybe we call this delta A, the size of each one of these little, the area of each one of these little Rij's, instead of a delta X. So now it's an area, we'll use an A. But that should just be delta X times delta Y, which we saw, maybe we put it together by writing it this way. That's certainly an expression for it, since delta x is b minus a over m and delta y is d minus c over n. So finally, we get it. This is it. This is, well, let me zoom back in here a little bit. This is saying if we added up all those towers and then took the number of towers to infinity, so there's not as much error up here, right? The little flat patch is more accurately approximating the surface. Then we get the exact volume under this surface but above Rij. Or above this rectangle R that goes from A to B and C to D. So we actually define this to equal we define this to equal the double integral over that rectangle R, denoted as I've written it here, two integral signs, and we just put the rectangle down here, of this function f of xy times dA, right? And so just like delta x turned into a dx above, delta a is turning into a dA here. And we call this the double integral of f of xy, you could write, over rectangle R. Okay, so that's a definition. I'm just going to make that note here. Okay. So I'd like to go through all this setup so that we have one good talk about it, and then we don't worry about this sort of technical view of things so much going forward, but it's really crucial to understand a lot of these basics in order to see things in more general terms and to use to problem solve using this math. So with that, maybe let's do one quick problem and then cut before another video. So let's go down here. By the way, I should mention, if this limit exists, we say this function is integrable. It can be integrated. It's integrable. So the fact that we say this limit equals something implies that it exists. But it's certainly true that that limit could not exist for some objects. I mean, if you're trapping like an infinite amount of volume, for example, all right, that limit wouldn't exist. And other situations. But for now, let's just use this as our definition. Know if that integral exists, if we can write down the volume, this integral exists, then we say that function f is integrable over rectangle R. And now, just like in Calc 1, we don't really ever use this limit in this class to actually compute volumes, but what we can do is we can approximate them or estimate volumes by taking a partial Riemann sum. Instead of taking all these things to infinity, take a finite number of divisions of your little rectangle and do this actual process by hand. So I want to see one of those really quick, one of these finite approximation problems. Let's call this, example. Let's estimate the volume of the solid below the graph of z equals 16 minus 4x squared minus 4, let's just say y squared, and above the rectangle R equals negative 1, 1 cross negative 1, 1. And let's do this by dividing R into 4 squares. So it's saying instead of taking infinitely many divisions, let's just chop it up into 4 pieces. That should be some approximation of the actual volume. And notice here I've written this rectangle in a weird way, but this is just saying that our A and B values, our X starting and ending points, are -1 and 1, and the Y values that always come after the X values in this notation say that our C to D is really -1 to 1 as well. So maybe here let's start first by actually drawing this scenario a little bit. Here's my X, here's my Y, here's my Z. Here we're saying our rectangle goes from -1 to 1 in both directions. So maybe I draw it maybe from here to here and here to here. There's my rectangle R. And so we notice this one actually already kind of automatically is going to look like it's divided into 4 squares, right? As divided by the X and Y axes. So this is nice and easy enough. It's just saying let's sample each of these 4 squares and see what height our graph is there. Take a little tower, a little rectangular prism of the same height, and use that little thing's volume, which is easy to compute, to approximate the actual volume over that rectangle. So here we're missing something though. We aren't being told how to actually choose those sample points. Let's say in this case, let's use the midpoint rule. This means we want to use the middle of each sample rectangle, right, of each little subdivision. You could also be told to use left endpoints or right endpoints. That would mean drawing this thing in, oops, sorry about that. That would mean drawing just the rectangle in really in 2D, this rectangle R, draw it in 2D. It's rough, but maybe we get the idea. And if I said sample using top right corners, maybe that would be for this rectangle, the sample point would be here. This one would be here. The bottom left rectangle would have a sample point here. Bottom right would be here, right? Those are the top right corners of each box. So I'd sample my points there. But in this case, I'm going to say we're using the midpoint rule, which means really, I'm not doing that. Let's see if I can easily undo all those. Instead, I'm doing these, the midpoints. That's really -1/2, 1/2, 1/2, 1/2. Sorry for my poor writing. 1/2 negative and 1/2 negative. And 1/2 negative 1/2. Negative 1/2, 1/2, 1/2, 1/2, negative 1/2, negative 1/2, 1/2, negative 1/2. Yeah. So those are going to be my midpoints of each one. And this is just saying, let's use our z value, our function value, let's let it be this stuff. So this is really like our function f of x, y. There's some graph over this thing. I don't know what it looks like. Maybe something like this. And we're finding that volume. Actually, we're approximating it. That's that surface I drew. So let me zoom out and let's come back over here and actually try to do this. This means we just need to take a function value at each sample point. Doing these in kind of a strange order. No real wrong way to do it, I suppose. As long as you get them all. Right, those are the function values at each of these sample points. Those are like the heights of my graph at each of these sample points. And then we multiply by the size of each little square that these came from. Well, each square in this case is just 1 by 1. So let's say over here on the side, our delta A, which is just delta x times delta y, is 1 times 1, which equals 1. So we're just really multiplying each of these by 1. That's our delta A values multiplying everything. Each one of these is the volume that approximates the volume actually under the graph and over that corresponding rectangle. That's not exact, but it's an approximation. And if we do this, I'll drop writing the ones, I don't need to do that, but I get f of negative a half. Would look like this. F of negative a half. Look like this. F of a half. Oops, forgot my square here, sorry. And finally, f at half, negative half. And you'll notice that the positive or negative in these terms doesn't matter because all the squaring. So these are really all looking like the same exact quantity. Let's just write out what we get here. We have 4 copies of 16 being added up. What is that? That's 64. We've got, notice each one of these is really a quarter, right? Each one of these guys is a quarter. Quarter times 4 is 1. We've got negative 4 copies of that. Negative 4 times 1. Add all these guys up. It's all negative a quarter, negative a quarter, negative a quarter, negative a quarter. That's just negative 4 copies of a quarter is negative 1. So it looks like we get, 64 minus 4 minus 1 equals 59. Well, that's what I get. That's my approximation of the area under this, the volume under this surface above the rectangle R. And that's how we would do this. We would say this is approximating the actual volume. Where we say the actual volume is this double integral of our function with respect to area. All right, so stay tuned for the next video. We'll pick up from here.